As you read this on Friday, June 13th, 2025, our sun is displaying a dramatic phenomenon. Today is not just another day in our solar system. Something extraordinary is unfolding above us, in the vastness of space, and it has the attention of scientists and skywatchers around the globe. Through the eyes of space observatories, a vast claw-shaped coronal hole has opened on the sun's surface. This gaping region, darker than its surroundings, stretches across a significant portion of the solar disk, and its unusual shape has captured the imagination of experts and the public alike. This isn't science fiction. It's a real event, unfolding 93 million miles away. The sun, our life-giving star, is reminding us of its immense power and unpredictability. A coronal hole is a temporary rift in the sun's magnetic field, unleashing a torrent of charged particles aimed directly at Earth. These holes act as open doors, allowing solar wind to escape at incredible speeds, carrying energy and matter across the solar system. This high-speed solar wind is racing toward us, far faster than usual. Scientists estimate that these streams can reach speeds of up to 800 kilometers per second, making their journey from the sun to Earth in just a couple of days. The coronal hole is now geo-effective, facing Earth, so its particle stream is on a collision course with our magnetic shield. This alignment means that the effects will be felt directly, with little to block or deflect the incoming energy. These particles will strike Earth's magnetosphere today, setting the stage for a significant space weather event. The impact will likely trigger dazzling auroras, but it could also disrupt satellites, navigation systems, and even power grids. What makes this event more intense is the formation of a co-rotating interaction region, or CIR, a shockwave where fast and slow solar winds collide. This turbulent boundary acts like a cosmic battering ram, amplifying the energy directed at our planet. The CIR will hit first, compressing our magnetosphere and priming it for the main storm. This compression can make our planet's protective field more vulnerable, increasing the risk of geomagnetic disturbances. This means the coming geomagnetic disturbance could be more pronounced and disruptive than usual. As we brace for this celestial event, scientists urge vigilance, reminding us that our connection to the cosmos is both beautiful and at times unpredictable. To understand what's happening on the sun right now, let's break down the concept of a coronal hole, a fascinating and sometimes misunderstood solar phenomenon that plays a major role in shaping space weather. Despite the name, a coronal hole isn't an actual hole in the sun's surface. Instead, it's a region in the sun's outermost layer, the corona, where the sun's magnetic field lines stretch far out into space, rather than looping back to the surface. This creates an opening in the magnetic field, not a physical gap in the sun itself. These areas show up as dark patches in ultraviolet and X-ray images taken by satellites because they're cooler and less dense than the surrounding corona. The lower density means there's less material to emit light, making them appear almost like shadows on the sun. Coronal holes act like powerful nozzles, channeling streams of charged particles known as the solar wind, out into the solar system at speeds 2 to 3 times faster than normal. These high-speed solar wind streams can travel millions of kilometers per hour, carrying energy and magnetic fields with them. The formation of coronal holes is closely linked to the sun's ever-changing magnetic field, which becomes especially dynamic as we approach the peak of the solar cycle, known as solar maximum. During this time, the sun's magnetic field is more likely to twist, tangle, and open up, creating more frequent and sometimes larger coronal holes. When these magnetic field lines open up, a coronal hole forms. Some of these holes are short-lived, but others can persist for weeks or even months, rotating with the sun and repeatedly sending streams of solar wind into space. As the sun spins on its axis, these coronal holes periodically face Earth and other planets, sending bursts of high-speed solar wind directly into their paths. This can have dramatic effects on planetary environments, especially when the streams are particularly strong. Coronal holes are a natural and recurring part of the sun's roughly 11-year solar cycle. They're one of the main drivers of space weather, influencing everything from beautiful auroras in our skies to disruptions in satellite communications and power grids on Earth. The current coronal hole is especially remarkable, not just for its sheer size, but for its distinctive claw-like shape. This unique structure allows an enormous volume of charged particles to escape the sun's atmosphere and stream out into space, making it a standout event for scientists and space weather forecasters. Its reappearance now, during a period of heightened solar activity, means that the solar wind it produces is even more potent and potentially disruptive than before. As we continue to monitor the sun, understanding coronal holes helps us prepare for the powerful effects they can have on our planet and technology. Imagine a vast, invisible river of particles, the solar wind, constantly flowing outward from the sun, bathing our entire solar system in a steady stream of energy. This wind is made up of charged particles, mostly electrons and protons that escape the sun's gravity and race through space at incredible speeds. Though we can't see it with our eyes, the solar wind is always there, shaping the environment around every planet, including Earth. Under normal conditions, the solar wind travels at about 250 miles per second. But when it bursts forth from a coronal hole, a dark, open region on the sun's surface, it can accelerate to over 500 miles per second. These coronal holes act like cosmic fire hoses, blasting high-speed streams of particles into space. Now, a surge of these charged particles, carrying with them the sun's magnetic field, is racing toward Earth. This isn't just a gentle breeze. It's a powerful, energetic stream that can have dramatic effects on our planet. If the magnetic field embedded in this stream is oriented southward, it can interact with Earth's own magnetic field in a way that temporarily weakens our planet's natural defenses. This allows solar energy to pour into our upper atmosphere, setting the stage for geomagnetic storms. As the fast-moving wind catches up to slower solar wind ahead of it, the collision creates a compressed shockwave known as a corrotating interaction region, or CIR. This region acts like a battering ram, pushing a wall of energy toward Earth. The CIR is the first to arrive, jolting our magnetosphere and causing immediate, sometimes unpredictable effects on satellites, navigation systems, and even power grids on the ground. When the main high-speed stream finally hits, it can buffet Earth's magnetic field for a day or more, keeping it in a state of constant disturbance and fueling ongoing geomagnetic activity. This isn't just a brief event. It's a prolonged disturbance that can last for many hours, sometimes even days, with effects that ripple through our atmosphere and technology. As the energy builds up and is eventually released, we witness spectacular auroras lighting up the night sky, but we also face the risk of technological disruptions, from radio blackouts to power surges. That's why space weather forecasters are on high alert, tracking these solar storms in real time, working to protect our technology and keep us informed as the sun's energy sweeps across our world. When this supercharged solar wind hits Earth's magnetic shield, it triggers a geomagnetic storm. Scientists classify these storms from G1, minor, to G5, extreme. Today's is forecast as G2, moderate but still impactful. G2 storms can cause voltage alarms in power systems, damage transformers, and disrupt satellites. While not rare, each storm's impact depends on the solar wind's characteristics and our technology's vulnerability. The energy dumped into our environment must go somewhere, often causing power grid fluctuations and satellite issues. G3 and above can cause widespread blackouts and severe disruptions. The current G2 storm will peak through Friday and Saturday, then subside to G1 by Sunday. Prolonged moderate activity can stress power grids and satellites, increasing the risk of failures. Scientists and operators are monitoring the situation in real time. Preparedness is key, even for moderate storms. A G2 geomagnetic storm has real-world effects. The power grid is vulnerable. Fluctuating magnetic fields induce unwanted currents, causing voltage swings and tripping relays. Already, regions like Michigan are reporting minor grid fluctuations. Satellites are at risk too. Increased radiation can cause glitches, resets, and increased drag, shortening their lifespans. Communications suffer. HF radio can be blacked out, and GPS accuracy drops as signals pass through a turbulent ionosphere. Industries relying on precise timing, like aviation and resource exploration, can be affected. Long pipelines may experience induced currents, accelerating corrosion and interfering with monitoring. Even railway signaling can be disrupted. While a G2 storm won't cause catastrophic failures, it exposes how interconnected and vulnerable our technology is. Each event is a reminder to strengthen our systems. The risks multiply during more extreme solar storms. Geomagnetic storms also bring the aurora, nature's light show. Charged particles collide with atmospheric gases, creating glowing curtains of green, pink, and red. Normally confined to polar regions, the aurora can be seen much farther south during a G2 storm. Tonight, millions in the northern US may glimpse the northern lights on the horizon. For the best view, find a dark spot away from city lights and look north around midnight. The display is unpredictable, but patience may reward you with a rare spectacle. Amid the technological risks, the aurora is a beautiful reminder of our connection to the cosmos. History shows the danger of massive solar storms. The Carrington event of 1859 caused telegraph failures, fires, and auroras as far south as Cuba. A similar event today could cause trillions in damages and months-long blackouts. Even less intense storms, like the 1989 Quebec blackout, have caused major disruptions. The current G2 storm is from a coronal hole that affected us last year, now returning during a more active solar phase. These events are inevitable, not hypothetical. Each storm is a test, reminding us to prepare for the big one. Recognizing the threat, agencies like NASA and FEMA recently ran a solar storm emergency drill. The simulation revealed that a severe storm could trigger cascading failures, weeks-long blackouts, communication breakdowns, and halted transportation. Our systems are deeply interconnected, and a power grid failure can ripple through every aspect of society. The drill showed we're not fully prepared. Urgent action is needed. Solutions include better forecasting, hardening infrastructure, and public education. Investing in resilience is essential to withstand a major solar event. The time to act is now. Today's G2 storm is a real-time test of our technology and preparedness. Our civilization is more sensitive than ever to the sun's moods. Ignoring space weather is no longer an option. It's as vital as tracking hurricanes. Space weather forecasters provide critical warnings, allowing us to protect satellites, power grids, and flights. As technology advances, our vulnerability grows. We must invest in science, forecasting, and resilient infrastructure. Watching the skies is about more than technology. It's about understanding our place in the universe. Each storm is both a warning